I missed something. Broadcasting it. Yep. Give me a second to orient the screen. It's not blurry, is it? Reasonable? It's a little blurry. Okay, let me try again. Hey, Clint. All right, let's see what we can do. That's worse. That's worse. Looks like that's about as good as it gets. All right. So before we were spinning about an axis and we were generating these disks, micro thin disks. Oop, wrong button. That happens. All right, there we go. So this time we're going to do it a little different. So what I want to do is consider, with a situation like this, rotating around the y-axis. Okay, where before we were rotating something like this about the x-axis to make the disks. If I rotate this strip right here, what I'm going to do is I'm going to make a cylinder. And if I collect a whole bunch of these, as I do that, say as I move X, then I'm going to get a whole bunch of cylinders and they're going to make something. Think roll of toilet paper. Okay, you have a bunch of cylinders that make an object. Okay, instead of a bunch of disks like stacking coins. So instead of stacking coins, we have the option of using cylinders. So then we have to say, okay, well, what does a volume of one of these cylinders look like? Well, we've all used like cans. And anybody here recycle? Often we peel the label off the can. Now, usually I destroy it when I do that, but if you neatly do it and you peel the label off a can, you get a rectangle. So cool thing about a cylinder, a cylindrical shell, is it, when you cut it and open it up, it's just a rectangle. Okay, and what used to be, say, the circumference of the top of the cylinder is now the length of your rectangle. And the height of the cylinder is the height of your rectangle. And even a piece of paper has thickness that is measurable. Okay, now we have these tiny, thin, barely measurable things. And so our thickness we call delta x, which in the limit turns to a dx. And if you consider my rectangle, right, I have a little chunk of the x value there that we refer to as dx. So looking at this picture, and let me get another version to blow up a little bit, what I'd like you to write down is what is the volume of that little rectangular slab. So, whoa, stop it. My mouse is out of control. All right. So here's a little blow up of that picture, maybe if I get that out of the way. So write down on a piece of paper right now, what is the volume of this rectangular slab? It's a thin box. All right, we have length, we have width, we have height. Put it all together in some order, whatever order you like. We can always rearrange. So bottom line, would you agree I have to multiply the length, the width, and the thickness together? Okay, so then we put them in some kind of order that's going to work out well for us. So in this case, the volume of my rectangle, and let's call that a delta volume because it's a little chunk of my total volume. And so usually it's written in the order of the length 2 pi times x sub I times the height f of x sub I. And then we're going to have our delta x. Oops, not delta d, delta x. And so thinking way back to beginning of calculus 2, this is one chunk of area. We want to add them all up and then take the limit as this guy right here goes to 0, which turns it into a dx. Okay, back to the original picture here. So what I want to consider is, again, here I'm revolving around the y-axis in this case. I want then a rectangle parallel, right? When we do disks, it's perpendicular, so we have a choice to make. We can go a different direction. When I do that, if you consider the revolution here, use a different color, the distance from the axis of revolution over to my rectangle, that's my radius of my cylinder, true? Like before, we have to consider, well, that is a horizontal distance, and horizontal measurements are done with what variable? X, okay. So there's my X as a radius, which comes out right there. Because we know circumference, right, is equal to 2 times pi times your radius. Radius here is the X value. So we're taking all of those pieces, imagine revolving this, which gives us that. That thing can be sliced open to give us that. And if we then add up all these suckers up, we get an approximation of the volume, which is like a roll of toilet paper. Now, because of the top curve, you could have a wildly shaped roll of toilet paper. It could be that we choose to only pick X values from like maybe there to there. And as we revolve, we would have like the tube hole in the center of the toilet paper. But it could be a solid thing too. Okay, so lots of options just like before, just a slightly different way of doing it. And sometimes what we'll find is using shells will give us an easier integral to take than using disks. Okay, so we're just going to play around with some examples, and we'll do actually both disks and shells today. The calendar said we were going to start 6-2 yesterday and continue it today. We're starting it today, which means we'll continue it on Monday. Okay, so I'll probably adjust some dates in the schedule. All right, let's try something. Let's take y equals x and y equals x squared, and imagine that region. So let's say they both intersect at the point 1, 1. Let's choose 2 different colors here. And I want to revolve around the y-axis. Previously, we would have to use what's called the washer method on this, which means we'd have a big R and a little r and some subtractions and squaring stuff. Remember we started setting up one like this at the end of class the other day with that crazy torus? That was a lot of work. Let's just see if shells might be easier here. So if I consider shells on this one, with shells, we want our rectangles from our graph to be parallel to the axis. Disks, remember, are perpendicular. So I'm just going to draw myself, here's my axis, a parallel little rectangle in there. And again, for my brain to wrap around getting an integral, I got to draw a whole bunch of pictures to make that happen. All right, so again, we're revolving. So when that little rectangle revolves, I'm going to generate a thin cylinder. It's going to look something like that when I revolve it around the axis. I could slice it there and open it up, and I'm going to get this rectangle out of it. And so the relevant components of this are the length of my rectangle for my volume, that's my circumference. Circumference is always 2 times pi times the radius. Okay, so I need to know that here. Let's see, thinking about the radius in this situation, the radius is going to be the distance from the axis of rotation up to my rectangle. And that is just the x value that I'm at. Okay, so some x value in this interval right here. Okay, so I'm going to have a 2 pi x involved here. I also, so that's across here. I also need the height of this thing. Okay, Let's see. Well, the top of it is the line y equals x, and the bottom of it is the line y equals x squared. Okay. So if the top is x and the bottom is x squared, what's the distance in between? It'd be x minus x squared, correct? And that's my height here. So I'm going to have to multiply by my height, x minus x squared. And then the thickness of my rectangular slab here, is that a dx or a dy? Yeah, it's a dx right here. Yeah, so then I'm going to have a dx there. And so now I can integrate that. Let's see, where should I integrate from? Where's my variable of integration, x or y? It's x, right? And x here probably started at 0 and end it at 1 if I want to rotate this area about to get a figure. So I'm just going to go from 0 to 1. Just for fun in a minute, we'll look at the washer method of this after to see if it's any better or worse. All right, we did the hard part. We set it up. We have an integral. So now we just have to clean up that integral and find an antiderivative. So give that a shot. Clean that up a little bit, come up with an antiderivative, and let's see what we get for a volume on this. So now we're picking up with that. Thinking pi over 6. Anyone else get that?
Yep.
All right. So I don't know if I've shown you this in class. I don't usually think much about lowest common denominators with numbers. I just think multiply, cross multiply, cross multiply, and there's my fraction sum or difference. So there's my 1/12 I got here. So it looks like it's pi over 6. So the things that we're trading with the disks, we have an area of a disk that we push through a height. The problem sometimes with that area, it involves squaring the radius. Okay, sometimes squaring an object makes it way more complicated. However, oops, wrong direction. In this situation right here, generally, if I'm rotating around the y-axis, I'm going to have x as my radius for that revolution. And then the height of the cylinder is always going to be a function of x too. So that's kind of like squaring something, right? We have a function of x times another function of x. So we can't really get away with it, get away without the square kind of thing happening, because bottom line is volumes are three-dimensional, right? Which means centimeters cubed. So somewhere along your calculation, you have to take centimeters times centimeters times centimeters. Your delta, whatever, x or y, that's always one of the centimeter measurements going on. And so somewhere in here, you have to create centimeters squared. And so now we have two different ways to do it. One is by looking at an area of the top of a disk. Now we have this other way of taking a cylinder and turning it into kind of a slab. And we have square units coming from that. Okay. Sometimes, however, this version of multiplying x's by x's can sometimes be easier than squaring some bigger object. It just depends. All right, let's go do some review. What I want to do is reinvestigate this object right here by using disks. So let's redraw it. Oops, I don't want red. I would like black, please. There you go. So if that's one and that's one, I've got my straight line to there and my parabola right there. And so we're still going to revolve around the y-axis. That's y equals x. This is y equals x squared. And again, I think it's in your best interest to label as much as possible without going too crazy. So you want to show some units, which axis is which, and somewhere on the page have which curve is which. And let's see, if we're going to go with disks, they have to be perpendicular to the axis. Since we have empty space between the axis and the object we're rotating, that means this is what's called the washer method. And in a washer, when you generate one, it's basically a disk with a cutout, right? And so to make that cutout, you need to know both the big outer radius and the inner cutout radius. So we have to decide which are those here in this picture. So let's see. From my axis of rotation to the outer part of my curve, that's my big R. What is the edge of big R going to be here? It's going to be x squared, right? Minus 0. Okay, so not much happening there. Little r would be the distance to this inner part there. And so what's little r here? X, okay. And so then this particular washer up there, doesn't that washer look a lot like a cylinder? It's just flat instead of tall, okay? So we kind of switch where directions go. That's going to look like the big disk, which is going to be pi big R squared minus the little one, pi little r squared. And so looking at our stuff here, that's going to give me a, what, pi x squared minus pi x squared. And then, now that's just the surface of this disk. We got to put in the height. Uh-oh, I got a problem. What's my variable of integration here? It's y, yeah. Usually I write that down right away so I don't put the wrong function down. Which means I can't use that version of it to find it. I have to rewrite these in terms of functions of x. So rewriting this guy right here, well, that's already rewritten. I just have to read it backwards. This one I have to rewrite as x equals what? Square root of y. Do I care about the negative square root of y here? No. Okay. So cleaning this up, big R is actually the square root of y, and little r is actually y. So now I have pi square root of y squared for the big radius minus pi y squared for the little one. This is one reason I usually draw this rectangle, and it's always a good idea to write dy or dx right away just to get yourself on the right version. So this, again, is the surface of that washer up there. That surface needs a thickness to give us a volume. That's our dy. And then we have to take a look at what are our boundaries of integration for y. And where is y going from? 0 to 1. Okay. So go for it. Clean that up and see what you get. So you have to come up with an antiderivative for that integrand. So we should get the same pi over 6 we got before. And then the question is, which is easier, the shell or the disk for a particular problem? Sometimes the shell is way easier, sometimes the disk is way easier, sometimes they're both about the same. Unfortunately, you never know until you've tried or you've seen it before. Okay. Let's try another one. Let's see. Your homework problems are similar to, where'd it go? I thought I had it here somewhere. Oh, back. This list here, what looks like fun? Just did 11. This last one looks like fun, but that might be too much fun to do yet. Let's take a look. Oh, 10 is just like what we just did. Ooh, let's try 9, absolute value. Okay. So we're going to take the region y equals absolute value of x and y equals 1, and we are going to revolve about the x-axis. New page, y equals the absolute value of x. And y equals 1. Y equals the absolute value of x, and we want to take the region that they bound. Let's see. And revolve it about the x-axis. And to do that, we are going to use shells. So if I'm going to use shells, then I want a rectangle that is parallel to the axis of rotation. relevant parts of the shell. So like my mistake last time, I'm going to right away come up here and say, hey, that is a dy right there. So I have to have stuff with respect to y to integrate. And so thinking about rotating that sucker right there, I'm going to end up with a cylinder in this orientation. I need to figure out what is the radius. The radius is going to be the distance from some point in that dy down to the axis of rotation. That's a vertical distance, right? So that's a y. So I'm going to have a 2 pi y here to get me around that cylinder. The distance across that cylinder, well, on this side right here, consider this line right here is y equals x or x equals y. And this side over here is y equals negative x or x equals negative y. All right, absolute value is a piecewise function. It's made up of two other functions. So this distance right here is horizontal. And so that horizontal distance right there, which is the height of my cylinder, is going to be looking at a function of y. So what will we call this side in terms of y? Well, it's just y. What's the other side? Negative y. Yeah, so that height is y minus negative y, which we can kind of look and say that's just 2y. So then I'm going to have times 2y for the height of my cylinder. And my integral variable is dy. That gives me the thickness. And so I have come up with my integrand. So again, I'm revolving around this way. This cylinder needs to slide from down here all the way up to there as we revolve around. Okay, spinning these discs out, these cylinders out. And so it looks like y is going to have to go from 0 to 1 here to make that happen. Right? As we slide that rectangle up and down. All right, clean that sucker up. Let's find an antiderivative. Let's see, we have 2 times 2 times pi, so I can pull out a 4 pi. And then I'm left with just what, a y squared? So I'm going to get 4 pi times y cubed over 3 from 0 to 1. So it looks like we get what, 4/3 pi in the end here? Or 4 pi over 3 if you prefer. And again, like we've seen time and time again with these, the hard part is the setup. So for me to set it up properly, I need to draw the region in the XY plane. I need to draw the rectangle, depending on whether I'm using shells or washers. It's going to be either shells parallel, washers perpendicular. And then I also like to draw the cylinders or discs I get to just make sure I'm putting things in the right spot. State your variable of integration right away to make sure you put your functions in terms of the right variable, and then start trying to put them together. Okay. Let's do another one. Yeah. Yes. Yeah. Yeah. So my general rule on showing work is if I can't do it in my head, I don't expect you to either. Now, I know a lot of the people that take this class are way smarter than me. I just happen to know more math. So I know people can do better things in their head than I can. But it's always a good idea to write as much down as possible to free your brain to analyze the problem. The more you keep in your head as facts, the less you have room to analyze, is my opinion and experience on that. The hardest part here is actually drawing the 3D shape that we generated here. And I think you should always try. I'm not a very good drawer if I don't practice a lot. But what is this shape going to look like? We only have just one little chunk of it here. Let's try and visualize that. So let's see, new page. We've got this triangle that we're revolving around. Ooh, it should look like a yo-yo, yeah. Oh boy, can I draw that? It's gonna have a flat top, flat bottom, right? Circular connection on each side. And then we have this central point that we're just going through. A yo-yo would have a little more thickness here, but it's the same idea. It should look like a yo-yo. So if I throw in some dotted lines here, there's some central point in here, and it comes down on the inside toward that point each way. So if I had a pencil and some lead, I could probably do some shading of this circle right here to make it look more 3D-ish, or on the outside. I don't know. That's the best I got. Anybody here good at drawing? No one's jumping up and saying, yeah. Yeah. The more I practice, the better I am. It just takes practice. All right, let's try another one. Let's see. How about, let's take a look at this last one. So this is one of your homework questions. It's the last homework problem in the section 2 set. The region shown here is to be revolved around the x-axis to generate a solid. Which method, disk, washer, or shell? Now, in my opinion, disk and washer are kind of the same thing. It's the same technique. Washer just has a hole in the middle. Could be used to find the solid. In either case, how many integrals are we going to need? So what we're going to do is we're going to worry about setting it up both ways, just like we did a minute ago, and try and decide what to do from there. So I am going to steal this image. Can I just copy it maybe? And paste. Oh yeah, nice. All right, so we're going to explore this guy right here. And we're going to need another copy of it in a new page. All right. Where's that other page? There we go. Okay, so since we are new to shells, let's start off with the shell method on this and see what that's going to look like. All right, so I believe it said x-axis. Let me remember. Okay, yeah. All right, so a couple things I do right away. First thing I do is I put that little curly arrow around the axis I'm rotating. And then I'm thinking, okay, shells are parallel to the axis. And so then I make myself a little parallel rectangle. So there's my rectangle. All right, so that particular rectangle, its thickness is a dy, right? It's vertical. So I know I'm integrating with respect to y. So that means I have to express stuff as functions of y instead of functions of x. Okay. So for each of these, I should rewrite them. So this one right here, that's going to give me x equals plus or minus the square root. Let's see, I stated that backwards. Y. Oh no, that one's already the way I want it, isn't it? Let me undo that. I'm thinking backwards here. I already have that one. X equals y squared. The other one, that's not going to be bad, right? I just add that 3y squared to the other side. And so for the other one, I'm going to get x equals 3y squared minus 2. So these are both sideways parabolas. The 3 in front of the y here means it was stretched horizontally, so it should feel narrower. The black one should feel narrower than the red one. And it shifted back to, which I can see the vertex there. All right, that's looking okay. When I rotate that, I'm going to end up with these thin cylinders. And let's see, I need my radius here. My radius is vertical, so it's just y. Right? the distance from the axis up to some y value in there. So that's my radius. As far as the height of this thing right here, it's got to be a function of y, and I've got my two things ready to do that. Is it true that the red curve xy's, remember x moves positive in that direction, is always on top of the black curve here? Yeah, so as far as x is concerned, the red curve in my region, which goes from -2 to 1, is always above. So that means my height of my cylinder here is always going to be y squared minus the other one, 3y squared minus 2. And that cleans up a little bit. Right, y squared minus 3y squared gives me what, -2y squared plus 2. And I think I have all the pieces I need to do my shells. Shells say you want to integrate circumference of this thing right here, which is always 2 pi times the radius, y in this case, times the height, parentheses, my height's complicated, -2y squared plus 2. And then we have the thickness dy. And what are the bounds of integration for y? Remember, it's always a good idea from now on to write not only your dy, but which variable you're using here. Because sometimes if I don't write that down, I might mistakenly try to go from -2 to 1, and everything's going to go to hell. Y goes from 0 to 1 here. Okay. All right. So I'm going to stop right there because the question didn't say what's the volume. The question said, if you use washers, discs, or shells, how many integrals do you need? Does one seem easier than the other? Okay, so we're going to stop there and we're going to move on to the next method. We're going to try and do this with washers or discs. So I have another picture of it here. Things to do. Note the axis of rotation right away. If you're told to do a method, make a note of that method. Let's see, I'm using discs, and I want to remind myself that discs are perpendicular to the axis. So, so that's kind of complicated here. Here, a disc runs from that black function down to the x-axis, but over here, the discs are designed differently. They're washers, and they need both functions. Is it possible to do this with one integral? No, it's not. We got to break it up. So we're going to have to make an integral for this region, and we're going to have to make an integral for that region right there, because they have different parameters in terms of the way the curves line up. So in terms of the disc/washer method, part of this are just straight discs with no holes in the middle, and the other part are definitely washers. Okay, so we're gonna have to break it up into parts. So let's just try setting it up. So let's see. Next thing I usually do is write down that this rectangle has a width of dx. So I have to have things as a function of x here. So that means I have to solve this guy here for y. So let's see, that will give me a -3y squared equals -x minus 2. Divide by -3, and I get y squared equals, say, x plus 2 over 3. I clean up the signs, and then I can take the square root, y equals plus or minus the square root of x plus 2 over 3. Okay, do I want the plus, the minus, or both? Yeah, I just need the plus here, so I'm just going to circle it, make a note. I just want the plus. All right. So other things to note. So I got that's dx. the distance from here to here is the radius of my disk. So I just want to picture one of these disks here. The disk is going to look like that. The radius of that disk is this function y as a function of x. Right there is what we just discovered. So it looks like my first integral is going to be the integral as x goes from -2 to 0. Right, that's 0 is when we switch stuff. I need the area, top area of the disk. That's pi times the radius squared. So pi times my radius, square root of x plus 2 over 3 squared, times the thickness of my washer, which is dx. So that's going to give me part of the volume. The other part's going to be a wee bit more complicated. I don't think I can squeeze it in that little space. So I think I'm going to get myself a new window for it. And let's see if I just go new window, paste. Is that still there? Excellent. All right, so we're halfway through the disk / washer method. So now we have to finish this one right here with that as a rectangle. So reminder, that's a dx. And I have to consider the black curve is y equals the square root of x plus 2 over 3. And that over 3 is inside the root. And the other curve would be what? Y equals the square root of x. And I don't need the negative part of the root. So big R is the distance from the axis of rotation to the furthest away piece. So whatever that number is minus whatever that number is. Well, that's just this guy minus 0, right? So this right here is big R, and it looks like this right here is little r. And the formula usually looks like pi times the integral of big R squared minus little r squared, in this case with respect to x. So let's see, what do we get when we do that? We're going to have pi times the integral as x goes from 0 to 1. And I know you're all capable of doing this step in your head, but I'm going to write it down anyway. Of the big radius squared, we have a lovely cancellation there, minus the little radius squared. Dx. And just before we take the antiderivative, we could clean that up a little bit, right? We could say that's pi, x goes from 0 to 1 of x plus 2 over 3 minus x dx. And we could even carry out that subtraction there before we take the antiderivative, which would probably be a good idea. All right, so I can't do this with straight disks, agreed? We got to jump into washers. So it's disk washers combined, and it takes 2 integrals to do that. There's no way around it. The other way only required 1 integral. So what do you think was easier here? Shells or disk / washers? Yeah, once I get used to setting up the shells, it is computationally easier, right? But we got to set it up. And bottom line, this stuff is hard, and you just got to keep doing it and trying to get used to it. So we have time to set up one more. Yeah, let's do one more setup. Let's see if any of these looked cute and challenging. Ooh, let's revolve around a different axis. We haven't done that. All right, let's take y equals x plus 2 and y equals x squared about the line x equals, I think -1 is going to be more exciting than 2. Let's find out. Let me copy part of that into a new sheet. We're just going to do the setup. Oh, I forgot. I said I was going to do that related rates problem. What do you want to do? We don't have time for that either. Okay, so we'll have to do the related rates problem next time. Did anyone solve that in their homework? Got a couple people did. Figured out how to draw the pictures? That's awesome. Okay, so we'll look at the related rate problem next time. We're going to look at the actually, I'm just going to shut up now, sort of. I don't want to rush anything. We're going to continue to work with volumes on Tuesday. We're not going to move on to section 3, which is trying to find out the length of a curve. That's pretty cool, but we're not going to do that. We'll hold off for a day on that. So next class, we're going to play more with washers and shells. I'll do the related rates problem so everyone can see it. I'm also going to redo the torus, the donut problem. And I had started it with disks. So I think I'll review the disk method and the shell method. And so I think between related rates, the donuts, and any homework questions, we'll have a pretty busy day on Monday. Okay. And then I think I'm also going to extend homework due date so you don't have to type in that password each time. All right, we're going to stop here. Thanks for playing. Keep trying. I'm going to do a study session tomorrow at 11 if anybody is around. And then other thing to note, I want to see a couple of problems on paper from every homework assignment from now on. I've already assigned, and Stanton pointed out, I forgot to publish I'm calling it a quiz. It's really just homework. It's not really a quiz, I guess. But I want to see your work on paper to see how you're drawing things, see your notation. So these two problems were from section 6.1. I'm going to pick 2 of the problems from 6.2 and ask you to write those down and submit them. And I think I wanted this one today. If you can get that in today, fantastic. If you need another day or help from me to get it in, let me know. I'll help you get it in. And either you could hand me a piece of paper or there'll be a little submit button up here if you have scanned it or take a picture of your phone with your phone, something like that. So however you can get that to me on paper, scanned, picture of your phone. I want to see some written work so I can give you some feedback on that. Because I'm afraid you have the same bad habit I do sometimes. You click on one of these problems and you sketch some ideas on how to do it, and then you kind of start typing in answers and hope you get it right. So I want to see some nice complete work on some of these. All right, I think Darren, were you saying something online there, Darren?
Yeah, could we get the today's homework pushed back?
Today's homework today's homework disappeared?
No, pushed back so we can have more
Oh yeah,
time.
I'm gonna move the date for both 6.1 and 6.2 to Monday. So you don't have to worry about a password there. But please don't put it off. Don't procrastinate. Do a little bit every day. If you can at least do 1 volume problem per day, things will start feeling better. All right, I am going to sign out here. You guys be safe, have fun.